Hello and welcome back. All right, today we're going to go ahead and take a look at the tree data structure. Now, last week we took a look at graphs, and a tree is really nothing more than a special case of the graph data structure. A tree is used to represent hierarchical data, that is, a data that has a parent-child relationship or a top-level and sub-level relationships. So if we take a look at like a directory structure, for example, if we have a folder right here, well, inside here you're going to have other folders and files, and these, if it's a folder, they could have other items in it as well, and this is a good use of a tree data structure. This is your hierarchical relationship where you have these top level nodes right here that store children underneath. And so those are really the two terms that you deal with a tree. There's this thing called the parent node, and then we have child nodes. And so a child are all of the direct descendants of the parent node. And so there's really only two conditions on a graph that in order for it to be called a tree. And that first condition is that there can be no cycles. The second is that every node has at most one parent. So nodes have 0 or 1 parents. So it can have no parent. Like in this case, this is the top level node, and there's actually no parent here. But you can't have an item that is parented to multiple places and still call that a tree. In that case, you're actually just going to have a graph. So if we take a look at some examples that we looked at last week, where you might have this, right? This is a graph because D has two parents, and there's also a cycle. So this fails both conditions. But instead, if we had A, B, C, D, and they were connected like this, well then, now we have a tree. Alright, so now the other important thing to note is that your relationship here is that you have your parent node and your child. And these are kind of relative to the place in the tree that you're looking at. If you notice that B is both a child node of A, but it's also a parent node of the node D. So your children nodes can also be parent nodes. And then when we talk about a tree like this very topmost parent node is referred to as the root node, sometimes the head node as well. And then these very, very bottom ones down here are considered the leaf nodes. And those are the nodes in the tree that are on that have the deepest path. And so when we talk about paths to the tree, we talk about from the parent down through the children hierarchy. And that's that path through that tree. And those are called leaf nodes. So let's go ahead and take a look at some other examples of where we would use trees and kind of figure out why they're useful. Okay. Alright, so if you take a look at just your desktop that you're looking at right now on your computer, the elements that are laid out on the screen, that's another great use of a tree. You have this hierarchy of layered items that you actually present to the user, and there's like this built-in Z order, or this kind of layered effect where certain things are on top of other items. And so if we were to draw the screen, maybe you have some icons on the desktop, and let's say you have another window over here, and it's an app. So you're on Windows, so you got your buttons over here. You may have another app that's kind of sitting, that's just overlapping. Well, each one of these items is actually going to be represented or can be represented with a tree. And so you might have like desktop, right? And then you have the items on here. So let's say you have the icon, and you have the other icon, these two things right here. And then you have your app. And inside your app has a bunch of different UI elements as well. We'll call this app 1. And then you have the other app as well. App 2. And it's going to have a bunch of UI elements that represent or that make up that application. And so if you store your data in a tree like this, you can do a lot of interesting things, like if your app moves, well, you know what? You can just move all of these things with it because everything is parented to that top level node. So that's pretty useful, pretty easy to see how we'd actually use a tree for that kind of data structure. Some other things that you'll see it for is that setup that I just showed you is exactly how you would do like graph trees on 3D modeling as well, right? If you're going to do animations on a joint, let's say you have a leg right here, and you have the top part of your leg, your knee, and the bottom piece down here. Well, you know, if these are actually parented together, we'll call them A, B, C. When you move A, you know, you can store the relationship here. B's positions based on A, and C's positions based on B. So when you move A over here, you can write a nice little algorithm that just updates A, B, and C in a really fast and efficient way. Some other uses for trees. Let's go ahead and clear this. Some other uses for trees would be representing expressions or like mathematical equations. So let's take a look at a really simple equation, right? 1 plus 2 times 3. Well, we can actually represent this expression as a tree, and so that we can actually evaluate it in the proper order. And so let me show you what it looks like. Well, let's just start with even 1 plus 2. We'll just do it even simpler. 1 plus 2. So how could you represent this as a tree? And so we know a tree has a parent. A parent and children. Okay, so an expression tree would have a parent, which is going to somehow represent one of these values, and then its children are going to somehow represent the remaining of values. So if we take a look at what's going on with 1 plus 2, well, we could have a plus node be this parent right here, and then we could have 1, and then we could have a 2 over here. And so, you know, if we just kind of visually draw it like this, just pull up this operator and put the operator, oops, that's a 2. Put that operator as the top level, making it the parent. You can kind of get a tree visual like this. And so when we evaluate this tree, we could just do one. Well, we could do the operator. Like, oh, we'll evaluate the left side of this tree, and then we'll evaluate the right side of this tree. And so this is the project that we're going to be working on over the next series of videos, is how we take a string like this that someone types in and convert that into an expression tree. And this will give us a feel on, one, how do we actually traverse trees? It's going to give us a little more information on a specific tree called a binary tree. And so a binary tree is a tree where every parent has at most 2 nodes. So it has 1 or 2 nodes, or 0 nodes. And binary trees are used a lot for storing like sorted information, because there's some really good algorithms that we can do to traverse a binary tree quickly. So for example, if we were going to store numbers in a binary tree, what you could do is you could say, hey, I'm going to store all of my values that are less than my parent on my left side, and all of my values that are greater than my parent on the right side. So if we have the numbers 1, 2, 3, 4, and 5, and I could pick arbitrarily where I want to start. I'm going to pick, I'll just pick 4, for example. I could use 4 as my root node. And so remember I said everything less than 4 I'm going to store on the right side, the left side of my tree, and everything greater than I'm going to store, or greater than or equal to, I'm going to store on my right side. So I'd put the 5 over here based on that rule. And then over here, I can write an efficient binary tree that's actually going to kind of balance this tree. And so what balancing means is that it actually tries to keep the left side and the right side, the depths of the tree, the same, or within one level of each other. And so if we were going to write a good tree like that, for the next set of numbers here that we need to put on the left side, that's going to be a 2. And then we'll have 1, and then we'd have 3. And so this would be a binary tree of sorted values. And so when we go to look for a value, let's say we want to see if the number 10 is in our tree. We can say, hey, I start at my root node. 4 is 4 less than 10 or 4 greater than 10? And so since 4 is less than 10, I know I need to look at the bigger numbers. So that's on the right side of my tree. And so I can traverse down this side of the tree. And at that point, I've saved having to search all of these elements over here on the left side. And so that's one example of why we'd actually use a binary tree to store numbers. So back to our expression tree. The expression tree, we're gonna learn how to do that. So we're gonna learn how to do traversal on trees. We're gonna learn about how to really how to write recursion on trees, because recursion is a very easy methodology to use when we're actually working with trees, because trees lend themselves so well to recursive patterns, because there's always this parent-child type relationship, and that continues up and down the tree. So in the next video we'll go ahead and talk a little bit more about expression trees, how we actually create them, and then we'll actually start digging into some code to actually create one, and then how to evaluate that expression tree after we've created it. All right, thanks.